Hello everyone and welcome to the course of fabrication techniques for MEMS based sensors clinical perspective. So I am Udipta, I am from IIT Madras and we will be today discussing the week 3 of this course. So this week 3 was majorly a continuation of the photolithography process here, and we somehow introduced the topic of photolithography, and then now it is kind of we are going in detail in each of the processes of so an important topic of mask alignment and then micro machining, talking about various types of etching in detail. Yeah. So yeah. So we'll directly go for the problems here. If any of you have any doubts, you are free to ask. And the questions, if there is any clarification that is related to the questions, you are free to write in the chat box or just unmute yourself and tell the question here. So yeah. So this is the question. A layer of 1 micron thick silicon dioxide is deposited on a silicon wafer, and the deposited layer is patterned using lithography and dipped in HF to etch the layer. Inspection after etching shows 100 nanometer of silicon is also etched with the silicon dioxide layer. What is the selectivity of HF to etch stop? Sorry, I forgot to unmute myself. So just to give you a bit what I was talking was that this week we are essentially last week we went through the top just introduced the topic of photolithography. Yeah? So now we will be going in detail on the different aspects of photolithography, particularly the mask aligner and essentially the micro machining techniques, which includes primarily the etching techniques. So yeah, we'll directly go to the problems, and the thing to note is that if you have any questions or any clarification that is needed in the question in any of the questions, just feel free to ask it directly, like unmute yourself and ask, or you can also put your queries in the chat box. So this is the first question, that a layer of 1 micron thick silicon dioxide is deposited on a silicon wafer. The deposited layer is patterned using lithography and dipped in HF to etch the layer. Inspection after etching shows 100 nanometer of silicon is also etched with the silicon dioxide layer. What is the selectivity of HF to etch silicon dioxide when silicon is considered as etch stop layer? So I'll give you around 5 minutes to solve this question, and then we can take up the we can solve it together. So I hope you guys are trying it. Yeah. So I think we can start solving it. If anybody has done it, just type out your answer in the chat box, and otherwise we will start solving it. Let's solve it. So essentially the selectivity is given by the rate, yeah, at which both the layers are getting the ratio of the selectivity H rates, yeah. So selectivity equal to rate at which silicon dioxide is getting H divided by rate of silicon H. So yeah, as both are kept for a same period of time, so the deposit is patterned. So it's 1 micron, so that means 1000 nanometer into T duration into and divided by the 100. The T assuming the T is the duration of duration it is kept in the etched solution. So here we get that it's 10 is to 1. So this would be the correct one. So if it is unclear, just tell me, then we can explain it together. But in a sense, the selectivity is basically the ratio of rates of H rates. Yeah. Okay, moving ahead, I have to tell that xenon fluoride for micro machining, xenon fluoride produces an isotropic feature after etching. Is the statement true or false? So there are essentially under bulk silicon micro machining here, there are two types of etching. Here we have mentioned about dry etching though. There are essentially two types of etching here we can do. One is wet etching, another one is dry etching. So both have two types here, iso and anisotropic. Anisotropic kinds, in which mostly the in wet etching the acidic agents are isotropic, while the alkaline are anisotropic. Here the bromine 3 or xenon fluoride are isotropic, but F fluorine based plasmas are anisotropic. So this you can essentially with this you can classify if such questions come on which uh, type of wedging the agent falls into, yeah, then you would be able to place it in that category. So here you see it's the so it will be true. Yeah. Okay, if there is no questions, then you can go ahead. So the lithography process has three modes here of exposure depending on the distance between the mask and the wafer. Those are contact mode, proximity mode and projection mode. Which statement is false regarding the exposure? So you have to tell which of the following statements are essentially false. the difference between the different modes of exposure, I think, I hope, is yeah, the PowerPoint presentations are uploaded each week, so I think it is available um, in the course page, yeah, in the problem solving session section. So I hope you know the different differences between the different modes of printing, different modes of exposure. Yeah. So like to give it a brief primer on it, it's like when you have like for example in contact, yeah, contact mode, uh, the mask, yeah, and the photoresist essentially is, there is essentially no gap in between, yeah, so it's kind of fully pressed according, like for example if it's a silicon wafer, this is the PR and this is the mask, and you have some illumination system here, maybe some lens too. This is contact, yeah, and then similarly for proximity it is that the mask and the PR will have some kind of gap in between. So this is the mask and similar kind of illumination, yeah. And what happens, this is proximity. What happens with the projection is that if you have a mask like this, yeah, then in between the silicon wafer and PR, you essentially have another lens to such that focus the light onto the silicon wafer, yeah. So that's the thing. Essentially here we have the similar kind of projection. This is what is projection system. So yeah, maybe with this primer the answering will be a bit more easier. So we can discuss, I think, yeah. So the effect of the first statement, the effect of diffraction of light is minimum for contact lithography. So just see, yeah. So whenever light will light will get light will have this features in mask, yeah, they will diffract light. but that diffraction of light, the effects of diffraction of light will increase with the distance it is there. So if you have a, so as light will hit these features and then it will bend, yeah. So this bending will increase essentially when we go farther from uh, the the point of diffraction, yeah. As it is very near and essentially touching also, so there will be minimal effects of diffraction, yeah. So this will be true. So in contact mode, the mask can be contaminated by the photoresist during alignment. So as they are in contact, it can happen, yeah. The mask will get contaminated with the with the photoresist that is placed in the silicon wafer. The contact mode cannot support mass production. So so here we see that the contact mode uh, yeah, so the contact mode cannot support mass production essentially because, yeah, we can make only the given only the given features can be made, yeah. We can't go for bulk of features, yeah. So here this will also be true. The contact mode of exposure can give better resolution than the other mode. So here we see in projection, yeah, you see that there are lenses involved, and we can, the resolution that it is available it is giving is because this lens system is something that is amplifying the magnification too. So this will be the false one, yeah, because projection method is far better in providing better resolution. Resolution means to differentiate between the different features, yeah, of a mask, yeah. So here these features can be made in the bigger mask, and that can be replicated in a smaller feature on the silicon wafer because of the help of the lens. So this will be the correct one, yeah. So yeah. Okay, so we'll go ahead. An array of cantilever is fabricated and characterized. It is found that it cannot meet the expected efficiency. What may be the reasons behind it? So okay, we'll discuss it. So here we see that yeah, cantilevers are freestanding structures here. So an array of cantilevers fabricated characteristics, it is found that it can meet the expected efficiency. So here we say that first option is cantilever structure may be destroyed in etching. So yeah, as you know that these are freestanding structures. Yeah, if they are etched more, then essentially we'll just so basically if yeah, this is the cantilever. Yeah, the thing is when you have isotropic etching, yeah, this starts it will start etching this part also. Yeah, and in some cases if you etch it more, essentially you will not end up getting this support. Yeah, and essentially will etch out these two. So in some conditions it happens. Yeah, so this can also be a thing. Cantilever structures may be buckled up due to stress gradient in oxide and nitride levels, so that you see. Yeah, when these are there can be generation of some stress, and as a result you will have some kind of deviations in the cantilever. Yeah, some bending or some things. And similar option is the cantilever structures may not be released properly during removal of sacrificial layer, and then there will be some stress developed too, and you will not get the desired shape of cantilever that you wanted. So essentially it should be all of this that basically can go wrong while fabricating a cantilever or an array of cantilever essentially. Yeah. Okay, so mention the fabrication process for achieving the following device using typical lift off process. So yeah, so you have to tell what all processes is essentially required here, and you have to make the structure. This is a side view, and this is the side view, and this is the top view, and you have to essentially provide the steps to fabricate this device essentially. And typically this should be done using the lift off process. let's try to solve the problem then. Uh, so initially you will only have a silicon wafer, yeah. So essentially what you can do is just dip this in HF such that the uh, native silicon dioxide can be removed, and yeah, the subsequent cleaning, yeah, after cleaning what we have, this silicon wafer. So what we will go for some deposition techniques like LPCVD, low pressure CVD, and then we can have a layer of silicon nitride over it, yeah. So going after that, we will what we'll do is have a spin coating and have the PR spread over the it, yeah. So now considering this PR is negative, so there are two types of PR, photoresist, yeah, positive and negative. So keeping it in negative with the like, if anybody can tell the difference between the positive and negative photoresist. So essentially the negative photoresist is something that upon exposed to the light it gets solidified, and then it will not be dissolved by the developer solution, while it's vice versa for the positive one. The positive in positive photoresist, the area which is exposed by light gets dissolved, yeah. So it's kind of, yeah. So what will you do is we will then design a mask, yeah. To design a mask, what will you do is we will design it such a way that if this is the mask, yeah, so in this, so it can have this kind of features. So this will correspond to this area, yeah. So here you will have chromium, yeah, and here essentially you have no chromium. So what will happen is then we will expose it using this method, yeah, lithography. And development. So what will you get is, continuing here, you will have the silicon layer, the connect, and then PR. So only the region that is getting exposed, so the no chromium region will allow the light to move, and the chromium layer will not. So you will have these portions being solidified and staying there. So what you will do is, on this you can put gold sputtering, yeah. So the gold essentially will be sputtered over everything, yeah. So if these are the PRs, so the gold essentially will form a layer over all of this, yeah. And then we will go for some PR stripping, which is essentially removing the photoresist. So in this process the photoresist will be removed, yeah, and while the photoresist is being removed, it will be removed along with the gold layer that is coated, that is over it. Yeah, so essentially finally what we will get is somehow like this is silicon nitride and AU over it. So this is how you will get the structure using the lift off process. So we are essentially lifting off this PR and only left with the other things. Yeah, if there is any doubts, you can yeah tell so. Okay. Good enough here. So we'll go ahead. Which of the following statements regarding wet etching is true? So uh, you have some, yeah, some statements, and you have to tell. Okay, so we'll discuss the answer then. Yeah. I hope you have done the question. So here, which of the following statements regarding wet etching is true? Is that anisotropy in wet etching is more likely to the surface reaction rate. So as you know that this anisotropic way in which wet etching is essentially very much related to the crystal planes and how this how the etchants can react to these different planes. Yeah, so it is more on the surface reaction rate limited regime. So yeah, the other options like diffusion rate limited is not correct because it is more surface reaction rate, and depending on the different crystal planes, yeah, it has different rates. So yeah, the same question. Yeah, in KOH, etching of silicon 111 plane gets etched the fastest. So essentially, it's the slowest one. Yeah, and HF etches silicon nitride much faster than silicon dioxide. So yeah, it's also false because HF is essentially important for silicon dioxide. It's a primary etchant for silicon dioxide, not for silicon nitride. So the question comes then, what is the common etchant used to remove silicon nitride? Yeah, these are some options. Just ponder upon them and tell the answer. Okay, so the answer would be that we know that the silicon nitride is a strong passivating layer, and it's a very good passivating layer essentially, and very hard to remove. But for etching it, the best, the common, most used etchant is phosphoric acid, and preferably hot phosphoric acid, which essentially etch it at the rate of 10 nanometers per minute. So problem it is on etch rates. Etch rates in silicon anisotropic etchant for different films are silicon. So different etch rates are given. So you have to tell what is the best mask layer for silicon anisotropic etching. So the criteria to choose the best mask layer is essentially to go and compare the selectivity. So the selectivity essentially is the ratio of the etch rates. So here we will calculate the different the different etch rates, the selectivity essentially. So selectivity. So first we will see the photoresist. The photoresist have 10,000. So so we have to compare the selectivity. So here we see that which one would have been the which would be etched less, yeah. So here we see that photoresist will have 10,000 nanometer per minute. So if we keep it for, so essentially if we keep it for 10,000, so it will go off, yeah. It will in 1 minute it will go 10,000 will be etched out. So the basic photoresist is there. So if we map it, it will first will be silicon nitride, yeah, with 0 nanometer per minute of etch rate. Then it will be silicon dioxide, I think so, yeah. So then it will be aluminum oxide, no, yeah, aluminum oxide, and the fourth one will be the photoresist, yeah. So this will be the order of what should be chosen as a mask for the following agent, yeah. So from the lecture we saw that it is desirable to have a 1:1 mapping from mask to wafer in a projection lithography system. It is called as the linear mapping. For this problem, let wafer to mask mapping be a quadratic function. We obtain that the following set of corresponding dimensions from mask to wafer. Yeah. 200 nanometer, 200 nanometer. So there is a mask to wafer like transfer ratio, the dimensions that they have given here. So what will be the line width in nanometer required on the mask if the feature is 300 nanometer on the wafer? So you have to tell what should be the line width that is there in the, that will be there in the so a relation between mask to wafer is given. So the question essentially will have the question basically asks that there is an unknown line width, but you have given the wafer the feature size at the wafer. You have to tell it in the what should be its feature size in the mask. So We know about this this 1:1, yeah. That means it essentially will have features around y equal to mx plus c, yeah. That it can be uh, satisfying this equation, but here we are given that it is like in one condition for our problem it is a quadratic function. So what we'll have, we will just make a table, maybe first mask and wafer, corresponding wafer. So for mask, if it is 200, here it is coming as 100, yeah. 450, it is coming as 150, 800, 200. So we have to find 300. So this is the question here. So for simplification, we can also take, yeah, y equal to x square plus c, unless let's see if it uh, agrees to our condition, yeah. So when y we will consider it as the mask, yeah, the mask one, yeah, this one. So I'll put 200 and a into x square, we'll put 100 square, yeah. So it will be 200 divided by 100 into 100. So it will be 0.02 equal to a. Let's see if it agrees to other things also, yeah. So 450, yeah, like put 0.02 into 150 square. So yeah, so it's 450 and 0.02 into 200 square. So for here we will write 0.02 into 300 square. It will be 1800. So the answer is 1800. So this is the next one. Mention the fabrication process for achieving the following device. Okay, so we'll solve it. So similarly, we will for this device too. Yeah, we will go for the process of cleaning and PR coating and then the lithography. Yeah, so if the mask design is concerned, we can essentially go for a mask design like this, in which you have alternative portions, yeah, and so on. So yeah, so this can be no chromium. And this will be chromium. Yeah. So light essentially will not pass them. Will not pass the chrome coated part. Yeah. So what we will get is essentially the device is looking such that because these are different planes. Yeah, essentially you will have one plane which is something that HS very slow, and this one is the 110 plane. Yeah, so and as a result, that's why you will get, if you do the etching with KOH, you will get such kind of uh, anisotropic etching. Yeah, and as a result you will have this kind of features. Okay, we'll go ahead. In an etching process, etch rate anisotropy can be given by 1 minus RL by RV. That means the lateral and vertical etch rates. What is the condition for undercut? So yeah, we'll discuss the question then. So here the first option, yeah, the lateral rate and vertical etch rate being same. So this is kind of the best condition for anisotropic etching, yeah, because essentially you will have ideal, because you will have A equal to 0, yeah. So this is kind of the ideal case. So yeah, not a case of undercutting. So in undercutting, what happens is the area that also needs to be stay, because yeah, for example, this is the PR, yeah. So you put your etchants. What will happen is that you will have some kind of uh, some kind of structures like this is the P area. So you will have yeah, with the lateral etching also there with along with the uh, etching in the vertical directions. Yeah. So in this is the Gaddis-Silva construction as there are if the lateral etching is more than the vertical etching, then you will have such kind of undercut. Okay, I'll go ahead now. Yeah. So this is the last question. So I will be staying here. If you have any doubts, you can ask me. And yeah, and that's all for today.